that. So yeah, you're welcome to follow along there. And just let me know if you run into any issues trying to access that. So thank you for the kind introduction. I'll do the quick version with maybe a couple of pictures to give you a bit of my background. So I did my PhD in geophysics at the University of British Columbia with a research group called the Geophysical Inversion Facility. And so we look at simulating geophysical experiments. I've done a lot of work, particularly in electromagnetics, and then working with those data to then try and estimate subsurface, to estimate models of the subsurface. And so with electromagnetic methods, we're sensitive to electrical conductivity, and so we can build up those models of the subsurface. And I'll talk a bit more about that today. So during that time, got very heavily involved in the development of open source software. And so that's going to be the focus of a lot of our time together today is on SimPEG. So it's an acronym for Simulation and Parameter Estimation in Geophysics. So in there, we've got methods and utilities for simulating a whole suite of different geophysical surveys, as well as working with those data. On top of that, we've built some educational resources on a website called geosci.xyz. And so this is a collection of open source textbooks and also Jupyter notebooks, where you can go in and actually interactively play and explore different physical simulations. And we'll show some examples of that today. And then I'm currently at UC Berkeley, connected with the Jupyter team, working on data science in the earth sciences. And then as Guillaume kindly mentioned, I will be heading back to UBC as an assistant professor next summer. And so continuing in a lot of the same research directions. So I'm sure some folks here have seen images like this before of what's kind of the basic ideas of what we're working with geophysical experiments. So what we have is we've got some sort of source that's going to input energy into the subsurface. And it's going to then, we're going to have responses that depend on the physical properties of the subsurface. So for example, here, if we consider something like electrical resistivity, and maybe we do a DC resistivity experiment where we inject current into the subsurface, those currents are going to flow. How they flow is going to depend on the resistivity structure of the subsurface. And then we can measure potential differences or voltages on the surface. And then from those data, what we want to try and do is figure out what the subsurface resistivity structure is like. And so there's a whole suite of different applications and problems that we can consider. Here's just a handful of applications. So things like groundwater or minerals. So minerals often, they tend to be conductive in a resistive background. There's also geothermal energy, where we're perhaps trying to find water that's hot water that's circulating in the subsurface. There's geotechnical applications where we might be wanting to monitor the integrity of a dam, make sure there's no leaks. Or there's situations where we've got contaminants and we want to try and map out where those are so that we can go ahead and remediate that land. And so if we look at just this collection of problems here, what do they have in common? So each of these applications require that we see into the subsurface without directly sampling. We want to map out where mineral deposits are or where groundwater is without drilling a ton of different holes to map things out. And sure, we can use some drill hole information, but those are really only point measurements when we actually want a much more distributed image, or really a 3D image of what the subsurface is like. And in this case, variations in physical properties, so these contrasts, in particular, we're going to focus on resistivity, can give us some insights about what the distribution perhaps of groundwater or mineral deposits are. So a few different experiments and a few different physical properties that we can consider. So you can characterize geologic units by differences in physical properties. So we could look at differences in density. We could look at magnetic susceptibility, electrical resistivity, chargeability, which is basically a rock's tendency to act like a capacitor. We could look at electrical permittivity, or in seismic, which I believe many folks here work with, elastic moduli. So as I mentioned, we're gonna take a bit of a look at the context with electrical resistivity. And so electrical resistivity, or its inverse conductivity, is a measure of how easily current passes through a material. So on the right, we've got a whole suite of different rock units or different materials we encounter in the subsurface. And you can see that the resistivity values vary over large orders of magnitudes. So we've got on the left here, massive sulfides, which tend to be quite conductive, all the way down to igneous or metamorphic rocks, which tend to be quite resistive, and things in between. And so the electrical resistivity, it depends on many different factors. It depends on the mineralogy. So what actually are those minerals that make up the rock, and can we pass currents through them or not? It'll depend on the porosity and what actually is in those pores. If we have saline water, which you might encounter in an oil and gas setting, in those very deep rocks, it tends to be quite salty. Whereas closer to the surface, or if we're looking for a near surface aquifer, that water tends to be fresher and will be more resistive. And so all of these factors will influence what the resistivity is. And so depending on what question we want to ask, if we're trying to find saltwater, freshwater, massive sulfides, or basement rock, and characterize these different units, resistivity can be one tool that or one physical property that can be diagnostic for us. So let's look at the basic experiment for a DC resistivity experiment. So the image on the right, we've got an example, and this is going to be a target that's an ore body, and the mineralized regions are less resistive than the host. So we've got a resistive background. The host rock is 200 ohm meters. We've got a resistive unit up here, but then these mineralized units that we're interested in finding, these are conductive. So what we're going to do is we're going to set up a DC experiment. And so DC is direct current resistivity. So we've got two transmitter electrodes, and these are going to inject current into the subsurface. And then we've got two potential electrodes, and these are going to measure voltages or potential differences. So we turn on the transmitters, and that's going to pass currents through the earth. And we're going to have a concentration of currents in regions that are more conductive, and the currents will be deflected around units that are more resistive. At interfaces where we have contrasts in conductivity or resistivity, sorry, I'll end up using those interchangeably. I'll try and stick to resistivity, but just know that conductivity is its inverse. And so you can use them interchangeably, and often they're used that way. And so where we have contrasts, we're going to have charges that build up at the interfaces. So if we're going from a more resistive unit into a conductive unit, we get negative charges. And if we go from a more conductive unit into a resistive unit, we get positive charges. And those are going to be then associated with the potentials that we measure at the surface. And so that's Coulomb's law, is that we get charges and they're going to produce potentials, and then that's what we measure at the surface. And so those are going to be the data that we work with. So to put this into a bit more context, I want to look at a concrete problem. And so we're going to look at an example of finding groundwater. And in particular, we're looking in Myanmar. And so the team here, we've got 7 of us down here. So Doug, he's at UBC, as is Ren and Devin and Joe. So they're all at UBC. Michael Maxwell is at Golder. Myself, I'm at UC Berkeley, and Sagi Kang is at Stanford University. So we have been working together on a Geoscientists Without Borders project. So this is a nonprofit arm that funds humanitarian projects, and it's facilitated through the Society of Exploration Geophysics. And so we got some support to run some training and provide equipment, and also work with locals to actually collect and interpret data in multiple villages to try and find groundwater in some of these villages that are water stressed. And so every year there's a dry season in Myanmar, and in some regions, and in particular the state that we're looking in Mon State, there's a number of villages where the shallow aquifers that they rely on to get water, they dry up. And so there's interest in trying to find deeper aquifers that they can access that will be more reliable and will still have water even in that dry season. And so the question that we want to ask, the first question we need to ask is, what are the physical properties that we're going to be working with, and what's going to be diagnostic of finding groundwater in Myanmar? And so in this case, there's often two aquifers that we might target. So there's perhaps a shallower aquifer. It tends to be on the order of, it can be sort of conductive. It just depends on what the resistivity of this host sand is. But the deeper aquifers that we're really interested in, they are in a resistive bedrock, and they tend to be slightly more conductive than the background. And so overall, what we're going to be looking for is the water-bearing regions in Mon State tend to have a resistivity of about 40 to 140 ohm meters. And so in this case, what we're going to use is DC resistivity, and see if we can use that to detect and locate groundwater. And so you can see there's a couple images here where actually folks are out in the fields collecting data. Okay, so now that we have these data, so we've got potential differences over a given region of the Earth. Now what we want to do is actually work with those. So we started with an image that looks like this, where we've just got a whole bunch of potential differences. And I'll show you how we build up this image. This is just one way to view DC resistivity data. So we've got potential differences, we've got voltages on the surface, and now what we want to do is try and translate that into now a three-dimensional model that describes the resistivities of the subsurface. So what we need to be able to do is we need to be able to run numerical simulations. So we need to simulate the DC resistivity equation. And so this is the governing equation here. And then we also want to be able to try and run an inversion. So if we're given data, now we want to go backwards. We want to try and estimate a model that's consistent with those data. And we're going to set that up as an optimization problem. And I'll show you a bit more about that later. So what we've done is, in order to work with these data, we developed a suite of Jupyter notebooks for actually running these simulations and inversions, both for teaching, so being able to go in, visualize currents, visualize some of the fundamentals of DC resistivity, but then also for working with these data. So to be able to go from the collected data back and try and estimate a model. And so what I want to try and do is actually pull up one of these notebooks to show you. So let's see if I might need to X out of here 1 second. Oh, was there a question?
No.
Okay. No problem. I guess quick question for folks. How many people have seen a Jupyter notebook, or is a Jupyter notebook brand new? Is this brand new to anyone?
I actually took a course about it, so I'm a bit familiar with the presentation. Yeah.
Yeah. So what it is Jupyter notebooks are an interactive computing environment. So you can combine text. So this is just some text that I've written, or other folks have written for this groundwater project. We've included some images and things like that. But then you can also include code. So here we've got some Python code where we've written some apps or widgets that we're going to work with to actually run DC resistivity simulations. So we've got examples like this where we're importing code. You can also just do simple things and see the outputs. And so it's a really great environment if you are new to coding well, and also even experienced. I use this every day in my work. For writing scientific code. And so if folks have questions about this afterwards, we can definitely chat a bit more about it. But what I want to show you is what we've done is we've built up some simulation tools that actually run the DC resistivity equations interactively. And so here we've got a suite of widgets where we can define the survey type, we can define the electrode spacing, build up our model. And then we can go ahead and look at a few different things. So here we're looking at a model. We've got blue is resistive. So we've got resistive background, and then we've got this conductive layer in between. And so this is somewhat analogous to what we might be looking for in the groundwater case in Myanmar, where we've got this resistive host and the region that contains groundwater is a bit more conductive. So we can look at our currents. So let's take a look. We're going to inject current from the A electrode, and it'll return at the B electrode. And so before I flip over to this, take a second, and if we know that this region is more conductive than the blue region, what do you expect the currents to look like? So build up that picture, and then let's take a look. So in this case, what happens is you can see that there's a bit of a concentration of currents in this conductive layer. Currents preferentially will flow through conductors, and you can see there's less of them that go into this deeper region because it's more resistive. That results in charges that are built up. Sorry, flipping through a few things there, but you can see there'll be charges that are built up on the interfaces, and that is going to lead to secondary potentials. And those are actually the data that we measure here. And so the data that we measure is then the difference between the M and the N electrodes. And then the apparent resistivity is just one way to quantify what those data are. And so we measure voltages, but the apparent resistivity is the resistivity that you would observe if the Earth was a half space. And so you can see by looking at this value, which is just over 3,000, it's in between basically the resistive value of the background that we see and the conductive value here. And so what that's telling us is that there is some influence due to this conductive layer that we're seeing in the data. If we then go ahead and look and let's see what happens now if we have a more resistive layer. So let's make this much more resistive than the background. And now you can see our apparent resistivity has increased. So it's now above the 5,000 of the background. And you can think through, before I change over to the currents, what now you might expect to see when we look at the currents. So in this case, because now this layer that we're observing here is much more resistive, the currents are preferentially going to flow in that top layer. So we have a much more a much higher concentration of currents in that top layer. And so this starts to give you a bit of an idea of what the data look like for a resistivity experiment. A couple other things to look at. So let's go back to a conductive layer. And so this star here is the specific datum that we're looking at given this setup. But what happens now if we move, for example, the A and B electrodes closer together? So we're seeing here the apparent resistivity is just over 3,000. So let's now bring the electrodes closer together. So we've got that's at 18. Let's put it at 5 here. Okay, so what you see is if we look at the currents, they're much tighter, they're much closer together because we've made our setup closer together. And the apparent resistivity is much closer to that 5,000. So if we have the electrodes very, very close together, basically what we're doing is we're just sampling that top part of the Earth. If we go much further apart, so let's maybe make this 50 meters apart. So they're off the screen, but you can now see that we're looking much deeper because we're injecting current from much further apart. And so this gives you an idea a bit of how we can maybe design an experiment to try and understand what the resistivity structure is of the Earth. Is if we first are sampling very close together, we're going to basically be sampling the top part of the Earth, and as we move further and further apart, we're going to be sampling deeper and deeper. And so that's then the data that we're going to try and use to actually estimate a resistivity model of the subsurface from those data. Now, did I see that there was a note in the chat?
No, it's okay. You can continue.
Okay, all right. Does anyone have questions?
Lindsey, I have a question. Yeah, so how deep can we go using these kind of tools?
So basically what the controlling factor is going to be how far apart can you get the electrodes?
Yeah, okay.
And so in general, that starts to get pretty complicated if you're going to try and lay out wire that's like 1 kilometer long.
Okay.
So a lot of it actually tends to end up being restricted a bit by logistics. And so the system that we brought to Myanmar, I think Thibaut's on the call, you might know this offhand. I believe that the line length was on the order of 400 meters. And so it tends to be, you tend to be looking, like the rule of thumb is basically a third to a half of the total line length. Thibaut, if you want to jump in and add to that, you're welcome to.
Thank you.
Okay. So we'll go back to the slides here. And if folks have follow-up questions on the notebook that I've shown, we can definitely pull that up again afterwards. So I want to talk now a little bit about what actually enabled what we were just looking at. Is that I'm clicking through buttons, we're looking at currents, we're looking at data, and how is that actually possible? And so what we're relying on for this is a lot of open source software. And so SimPEG is an open source software package. That's this logo here. But I've put in a suite of logos that we're relying on in the SimPEG ecosystem. So SimPEG is written in Python, so we rely on the core utilities of the Python language. But then there's other packages like NumPy, which does numerical arrays in Python. So if folks are familiar with MATLAB, a lot of the same functionality that's in MATLAB is in NumPy. There's also Jupyter, which is what we were using to do interactive computing. There's other tools for machine learning like scikit-learn. There's tools for parallel computing like Dask. And so we're relying on this entire open ecosystem of tools that are freely available and developed by scientists, developed by folks in industry, who all have different scientific problems that they're working on. But we're able to leverage and build upon those tools to actually go ahead and run these simulations and inversions. And so there's kind of two aspects of this that I want to focus in on. Is open source software is more than just the code. So there is the code piece, which is extremely important, and that's what we're actually using to solve our problems, but there's also the community aspect. And so I want to walk through a bit of how these two aspects of open source software interplay to make this a pretty exciting space to be in. And so just to show a couple images here, so this is the SimPEG website. So if you're curious to find a little bit more about SimPEG, this is the URL here. And this is the team of current active contributors, and we're always interested in welcoming more, either if you want to just come in and start getting familiar with SimPEG, or if you want to start contributing code, and anywhere in between. So how do we actually go ahead and solve the DC resistivity equations? So in this case, what we're doing is we break up the Earth into a bunch of voxels, and we define, to do that, we define a mesh. So I've shown an example here of a 2D mesh. So we build up, define spacings of our mesh, we build this up, and then we have all of the differential operators that we need. So for example, solving the DC resistivity equation, we need we need the divergence, and we need a gradient. And so once we've defined the geometry, we then have access to all of these differential operators to go ahead and actually build up the equations. So once we've defined a mesh, what we're going to do is we're going to discretize the equations. And so in this case, we're going to use matrix representations of all of these operators. So we use what's called a finite volume approach. And there's some great resources that I'd be happy to point folks to if you're interested in getting a few more of those details. But basically what we're going to do is just going to represent this as a matrix equation. And so we've got the potential, which is what we're going to solve for. Q is the source term. Sigma is the conductivity of the subsurface, so in 2D or 3D. And then here now we've got the gradient and the divergence, and those now we're just going to represent as matrices. So this is what the discrete equations look like. And then this is actually what it looks like if you implement it in SimPEG. And so once we've built that mesh where we've got that geometry, we can then go ahead and build up the differential, all of these operators, and construct our system of equations, and then go ahead and solve that. And one thing that's kind of cool, you'll notice here, there's nothing that's actually specific about this being any given mesh type. And so what I showed you in the previous slide is called a tensor mesh, but we also have tree meshes or cylindrical meshes. And as long as those are implemented with the common set of methods and properties, we can actually go in and swap out and use different mesh types. And so this is one of the things that sort of thinking towards when you hear about sort of modular software design, or an API, an application programming interface. These are the kinds of things that you try and think about, is basically how do you design software so that you can plug in new pieces and extend them and do new things without having to change your entire code base. So that's the high level version of actually how we solve the DC resistivity equations. So that gives us that first step where we want to be able to actually simulate equations to sort of predict data. The next step that we want to do is actually solve the inverse problem. And so we have data and we want to estimate a model. We want to estimate what that conductivity structure is. And so in this case, we pose it as an optimization problem where we want to minimize some data misfits. So DOBS is our observed data. F of M, this is our forward simulation. So what we just wrote on the last slide of how to predict data. And then here we use some weights that we're going to use to incorporate sort of a noise model or estimated standard deviations on our data. And so this is basically just a measure of how well are we fitting our data. If this is 0, that means we fit our data exactly. We never are actually going to be able to drive it to exactly 0. So we want it to just be, we want it to be small. And so that, because then that means that your model is representative of your data. Now, in general, we're dealing with ill-posed problems. That means there's many models that actually could fit the data. And so what we want to do is then impose some constraints on that. And so we do that through regularization. And so, for example, if we maybe have a reference model, if we know what the background resistivity is in the area we're in, that's all information we can incorporate there. Typically, we ask for the model to be smooth, so not large gradients between cells that are adjacent to each other. But there's a lot of different things you can do here, thinking about perhaps you actually maybe want sharp boundaries and things like that. So you can go ahead and replace and change the definition of this regularization function. So then we combine these two. So we want to fit our data and we want some regularized model, so something that's ideally geologically reasonable. And then we go ahead and we minimize this. And the result of the inversion is then the model M. And so I've talked about this in the context of DC resistivity, but there's a whole suite of methods that we've implemented in SimPEG. So we've got gravity and magnetics, induced polarization, which is sensitive to chargeability. We've got electromagnetics, and with fluid flow, we've got Richard's equation. And so the high level process that I talked about before, where we're running this optimization problem, it tends actually to be a fairly iterative process, as we might have some estimates of our data and uncertainties. We know our governing equations, and maybe we know a bit about the geologic structure. We would then want to go ahead with the inversion and potentially be going in, changing things like different weightings and things like that as you're actually looking at the results that you get. So that's the code, is we've got tools for simulating and inverting a whole suite of geophysical data types. But in order to actually make this happen is really the group of people who are involved in the development and the practices we adopt around that. And so I kind of broken this down into two aspects where we've got software practices. So things like versioning the code, tracking changes, testing the code, which is very essential when you have multiple people in a given code base. And it also lets you confidently make changes when you've got checks in place to make sure that what you've done hasn't broken things that used to work. We use what's called a pull request to actually suggest changes. And so that allows folks to actually go in and we can peer review each other's changes before we accept them into the code base that we distribute. And so a lot of this is common sort of software engineering practices. And they're really facilitated by a number of tools, like, for example, GitHub helps us achieve a lot of these things. But another aspect beyond just working on the code itself is actually bringing the team together. And so we have weekly meetings. In fact, we just wrapped one up about an hour ago, where every week we get together for about an hour, chat about changes, chat about research problems that people are working on, and what developments we might do to actually make that happen and make it easier for them to do computationally with SimPEG. Those are all recorded and they're posted on YouTube. So if you ever want to follow along or hear what folks are up to, you're welcome to do so. The links are available through the SimPEG website. And we always welcome people to come and jump in on Discourse, which we use for, it's a forum for question and answer, as well as Slack. So a lot of us are in Slack on a daily basis and happy to answer questions there. And also, if you watch a meeting or looking through some of the notes and have some suggestions or ideas, we're always welcoming those. To give you a sense of a bit of the scale and some of the other impacts in the broader community, I've got an image here where we're just looking at some of the analytics on the SimPEG documentation. And so this is for 1 year as of today. And so that's over 13,000 people who have looked at the website. Now, that doesn't mean that they've all used it or all downloaded it, but it's an interesting metric to see that there are people who are interested in exploring some of these things. Another thing that I think is quite exciting to see is a number of papers that have come out that SimPEG has enabled some of that research. So Thibaut, who's on the call, or at least was a little bit ago, but I think he still is, he's done some really cool work looking at joint inversions. So combining multiple data sets to produce a consistent geologic model that's consistent across multiple physical properties like gravity and density and magnetic susceptibility, for which you would use gravity data and magnetics data. So that's some exciting, very recent work in the SimPEG community. One of the things I'm also extremely excited to see is that there's actually papers that are being written that use SimPEG that don't necessarily involve any of the core team. And so I think that's a really exciting metric to see that if other people are actually able to pick up and use some of the work that the SimPEG community has done, it's useful beyond just the research applications that we're currently working on. And so one link that I've put down here, this github.com/SimPEG research, this is a GitHub organization where actually a lot of the active research projects are putting code. So you'll see a lot of repositories there that contain a lot of notebooks for active research projects or that go alongside publications. And so a lot of the publications that have been done by folks in the SimPEG community will have code associated with it. So if you want to get up and running or sort of play around with their results, you can. So a few resources that I've mentioned and that are also built on top of SimPEG. So there's the geosci.xyz website that I mentioned, where we've got a couple sort of textbook style resources for geophysics. Then within SimPEG, we've got the documentation. So it's just docs.simpeg.xyz. We've got our discourse forum, Slack, which we use for real-time chat. We recently did a tutorial as a part of the Transform conference, and it focused on DC resistivity. So if you'd like to do a bit of a deeper dive into simulations and inversions with SimPEG, this is a great resource. It's a 3-hour tutorial with the associated notebooks that you can work with and invert real data in a mining context. And then the other community I wanted to point out, which is how I actually got connected with Julio, is the software underground community. And so this is a broader community of folks who are in the geosciences, interested in computing, interested in machine learning. And so if you haven't had a chance to take a look at it, I'd encourage you to check it out. It's a great community of people. So I wanted to just circle back and look at a handful of the problems that we had pointed out earlier on. And we pointed out that these applications have in common that we need to see into the subsurface without direct sampling, that physical properties can be a tool that provide insights. So in this case, we focused on electrical resistivity, but we've got other examples where density and other properties like magnetic susceptibility are particularly important. But I think looking sort of at a bit of the bigger picture, when we look at challenges like groundwater, natural resources, tracking contaminants, and our impact on the earth and on the subsurface, each of these questions and the challenges that we're trying to solve are much bigger than any one person and even any one scientific domain. Geophysics is just one piece of the puzzle. We need to know about geology. We need to know about hydrology. We need to know about sort of impacts with society in order to make an impact. And so I think this is where open source software and resources have a really exciting role to play, both in the code and resources and tools that are developed, but also the communities of researchers that they bring together. And I've found that extremely valuable and rewarding in the SimPEG community, as well as in the software underground community, is the exchange of ideas that you get in working with other people. The exchange of ideas and new collaborations that result as you find people who have different skill sets that complement yours and different knowledge that complement yours that can help make progress on questions that neither of you could have done alone. And so with that, I want to give a shout out to many folks in the growing SimPEG community. None of this would have been possible without their contributions, involvement, and dedication to making useful tools for the community. And I've got a couple links here to, or handles of where to find me on the internet. And again, the talk is available here. And so I'll stop talking here and we can open it up for any questions that folks have.
Well, do you have any question, guys?
Lindsey, first of all, thank you very much for this great talk. And well, I have not really a question, well, it's a question, but it's something I would like for everyone that attended today to get from this talk. What do you think? Well, I think it's important, but what's your opinion about open source software? I think it's something really important, and people, students on undergrad university, we should like take more advantage of it. I don't know, what do you think?
Yeah, absolutely. So I think, well, one of the big motivations that we had for SimPEG is really, a lot of geophysics has traditionally been very closed source, people holding code close to them within a company or within an academic group because it gave a competitive advantage. But at this point, a lot of the methods like solving Maxwell's equations for electromagnetics or solving the DC resistivity equations, those methods are now well known. And by all of these groups holding code back, first of all, if somebody wants to implement a new idea, in many cases, you have to start from scratch. Whereas if you have open source tools, you can pick up the work that other people have done and run from there. The other thing is that if everyone sort of develops their own independent solutions, it's very hard to have those things be interoperable and working together. And so if we're looking at these questions where you might need to combine multiple data sets or knowledge from multiple domains, if you've designed everything with your single set of assumptions, it makes it really hard to cross these disciplinary lines. And so I think you know, for being able to build upon other people's work, integrating with other tools, but then also building upon and finding the right collaborators and the people that have knowledge that complements yours. So you don't need to necessarily know, you know, everything about, you know, from the geology all the way to numerical geophysics and inversion and machine learning. You can combine your skill set with others to make progress. So.
Yeah, I think that's very important to say because, for example, here in Mexico, in our scholar system, for example, sometimes you can get the idea that you have to know everything to do something. And it's very important that you say that it's not like that, that you can use what other people are already have already done, and that, yeah, it's just like that, that you don't have to develop all by yourself again, right? So I think that's a very good comment, Lindsey. Thank you.
And I would say,
Would like to comment or something? Si alguien más quiere comentar o hacer una pregunta, con mucho gusto la pueden escribir o la pueden decir por acá y los ayudamos a traducir si quieren o lo que sea. No sean tímidos, chicos. Don't be shy.
Javier Ábalos.
Excellent and interesting presentation. For me, represent a new vision for the use of the data in Python is incredible. Well, I have a question. My professor of electrical methods told us about the near or what-off measurement between the receptor. This is important for resolution of images that result. What is the importance of this for you?
Let me see if I understood your question. It was, are you asking about including wellbore results?
Yep. Because I see the difference of two methods. Schlumberger and
Wenner.
And Wenner.
Yeah, so wellbores can absolutely provide very valuable information. So there's a couple ways that can happen. I mean, if you have electrodes down a wellbore, now you actually have a more complex or a survey geometry that will let you get currents deeper and perhaps closer to your regions of interest, so you can get a richer data set. But even without that, having knowledge about the lithologies, so if you know that, for example, there are clays that are conductive and maybe there's granitic basement that's resistive, all of that information you can work to actually include in the inversion to get a better result. Is that, you know, the more prior information that you can bring, the better off in general that will be trying to get out a geologic interpretation from those data.
Okay, thanks.
Okay, so here there is another question. Well, he says, I have two questions. How someone without a coding background can contribute to SimPEG, maybe translations of manuals or tutorials for a broad audience? And the second one is, and what are the advantages of using Python versus other programming language for these specific geoscience applications?
These are great questions. So to your first point about how to get involved, there's a lot of different avenues, and so you definitely don't need to feel like you have to be an expert programmer before you start getting involved in these projects. And so the two things that you pointed to, translation of documentation or manuals and tutorials, are a great place to get involved. So one of the things that I think is actually an extremely valuable contribution is, if you're interested in learning about these, is working through the current tutorials and seeing where you get stuck and what things are clear versus not. Is because some of us, once we've been involved in the project for so long, you don't know where people get stuck or where our explanations aren't clear enough. And so actually even just working through those and asking questions is a great first step. And then from there, if you have your own application and want to write a tutorial, we'd be very happy to have those contributions, because they're extremely valuable and we're always in need of more documentation and examples. And if you wanted to translate materials, that would be really, really exciting. I'd be very happy to work with you to select, a couple high impact examples to perhaps make that, make some waves and be useful to you and others in your community. In terms of advantages for using Python versus other programming languages, there's a couple things. So first, Python is open source, and so it's easy to pick up and use. There's tons of tutorials around it. And it also means that if you develop some code and you want that to be proprietary or not, you have that option. But there's also other languages. So Julia, for example, and R are also both open source languages that have good communities around them. And they do some, Julia is very high performance sort of numerical computing. R, there's lots of statistical, it's more in the statistics community. But I think the other thing with Python is there really are a lot of geoscience tools and packages that are written in Python. So SimPEG is just one of those packages. We do simulations and inversions. But I don't know if folks have seen the Fatiando project. So that is led by Leo Ueda, and now a whole team of contributors there. And they've got tools for processing magnetics and gravity data, also a bunch of visualization tools. There's a package called OBSPy, which does global seismology. And so there's a whole ecosystem of tools that work well together that are written in Python. So that can be a real advantage.
Yeah, guys, well, from my personal experience, I started like this, learning Python like 4 years ago through some tutorials from Agile Scientific back on those days, Matt Hall and Evan. And then I joined Software Underground, I think 2 years ago after my first hackathon. I mean, I got into a hackathon without knowing a lot about Python. So basically I was just there like, I know how to do that. I know how to use Welly, so I can give you a hand with that, guys. And then I started like learning more from these guys, from people like Lindsey, from like Matt, like Robert, Luckeny. They are really good. And every time I have asked questions on Software Underground, hey guys, do you know how to do this? Do you know? I am trying to create a buffer from a wellhead coordinates. Any idea? Then you discover there's a bunch of packages already that you can use. I have never used SimPEG yet, but I have used LAS.io, Welly, Delis.io, GenPy. I have used, there's so many things out there, and there's a project, if I am not wrong, there was a project on the hackathon to integrate the whole ecosystem into one, so we can have like a package having all the packages, if I am not wrong about that. And there's events every year at least. There's the Transport 2020 that was on June. Lindsey presented there, if I am not wrong. There's a tutorial on YouTube about SimPEG with Lindsey presenting about it. One of the intentions we have with these talks, guys, is to encourage you, inspire you, motivate to start learning some Python, some R, some Julia, to create a community, to start making one in Mexico, because there's not a lot of people right now doing it. During last Transport, I always say it, but we were like 3-4 people from Latin America, and it will be awesome that we could have more people. I know some people from UJAD already doing some stuff, and that's like one of my personal goals here with the community, like to encourage you guys, and I hope these kind of talks really, really help you.
One other community to point to, I was fortunate last year to give a talk in Colombia at SciPy Latin America. So there is a growing community of folks who use scientific Python. They're not all geoscientists, but there's a great set of, I believe all the talks were recorded. I'll try and find the link while we're chatting here. And so that's another great resource. And cool community that I encourage you to, you know, if you watch some talks and find somebody who gave something interesting, people in the open source community tend to be pretty open and excited about connecting. So.
There's a question.
Hola?
Daisy, yeah.
You can hear me? Yeah?
Yes.
Okay, I think this is a simple question, but I will do it. How do you choose the arrangement for work? I mean, for find out something specific in the subsurface. I mean, you always do a simulation, or you do something calculus, or what do you do?
That's a good question. And so actually, and it's not, yeah, I mean, so simulation is an important piece. So often what you do is if you have a sense of roughly what a conceptual geologic model is that you're looking for. So in the case of the aquifer, we sort of knew that we're looking for a more conductive unit in a resistive background. And so we might go ahead and run a simulation and make sure, first of all, that, for example, if we ran just a resistive background with no aquifer, and then a resistive background plus an aquifer, we run those two simulations. Is the difference between the data that we observe in both of those, is it significant enough that we're confident that we'll see we'll see the aquifer in the data? So for example, if the difference is 200%, we're pretty confident that this survey is going to be sensitive to that physical property contrast. If it's only 5%, which is probably pretty close to our noise level, then we need to be, we'll be more skeptical that that survey will work. So that's sort of a first step. That's detectability, is can we actually see the feature that we're interested in our data?
Mm-hmm.
The second step that we often go to then is saying, okay, if I'm confident that I can see this in my data, let's actually now run the simulation so we get synthetic data, and then let's actually put that into the inversion and see what kind of model it is that we get out. Because that we're never going to get back, you know, clean straight layers exactly in the right location. We get back sort of a smooth version of the world. And so what does that inversion actually look like? And does it have the right resolution to sort of characterize what it is that we're interested in?
Oh, okay. Thank you.
Welcome.
Eduardo Montalvo has another question. Says, here in southern Mexico, the main approach to geoscience is related to things like oil and gas. That's true. Mm-hmm. So I'm wondering if maybe any of you know about similar open source projects related to closer related to oil and gas simulations. Maybe something like production estimation or something like that. I know a guy from Malaysia, Johannes Moore. I don't know if you know him, Lindsey. He's on Software Underground too. He's writing a package for reservoir simulation. He's just like showing some teasers right now, but that package looks really nice. That's one simulation package I've seen. I don't know if you know something like Eclipse or something like that in Python.
Yeah, that would be a good question for the Software Underground community. Is that there's, I mean, some of the ones that you mentioned, well, yeah, so packages like Welly, I know that there's packages for some aspects of seismic. I'm not quite as familiar with the seismic open source space. OBSPy is a fairly well-known one for processing, but it is more targeted at sort of global scale seismology, although there's enough overlaps that there might be some utilities in there for you. And then, I mean, if you're looking at gravity or electromagnetics and sort of more the simulation and inversion side of things, there are folks in the SimPEG community, and some of the work that I did during my thesis looked more at simulations and settings with steel-cased wells, where we're maybe trying to map out hydraulic fractures and things like that. But yeah, I'm not as familiar with the reservoir simulation or kind of the seismic landscape in Python, but the software underground community would be a good place. But I see, Julio, you've put some links in there too.
Yeah, I'm trying to find a specific post, but can't find it right now. It has so many posts, but if you go into that link, you can like stalk him. I mean, see what he's posting, and then you will find what he's doing with the reservoir simulation. He's the only one I have seen so far, or through my contacts, that's the only person I know that is working on it. I can ask on Software Underground, see what people can tell me about it, and I tell you about it. Or yeah. Okay. Any other question, guys?
Oh yeah, good point.
Yeah. I never read the project at all. Thank you, Devout.
Well, there is someone here saying there is also the Vito project for seismic simulation, and he already posted the website, so everyone can look at the chat and see all the questions that have been done during this conference, and follow the links that Julio and that Lindsey have shared with us.
Okay, if there's no more questions or any other topic to talk about, I will like to...
Yeah, Julio, I'd just like to say something like, because most of our audience are students or recent graduates, I would like to say that the most, well, I found very relevant of the presentation that there are so many ways where a geophysicist can work on. I mean, not everything is oil and gas industry. As you saw in the presentation, there are other many fields where you can develop, for example, geothermal, mining, or other industry. And because of this recent downturn in the oil and gas industry, probably it's very hard to find a job right now in the oil industry. So I would like to invite you guys to see what are the differences, what are the different ways where you can be focused on and try to understand and try to learn another skill so you can be easily incorporated probably to the workforce.
Yeah, that's...
As Guillermo said, it's important to remember you that all these talks are made for you mainly as students to help you to learn something else and to open your perspective and see that there is something else besides oil and gas industry. And yeah, I mean, take all the resources that you have at your hand to improve yourselves. And we really hope these talks are very useful for all of you. And if anyone have another question, don't be shy and share it or comment. We'll be very happy to answer.
So, Lindsey, I had a question for you.
Mm-hmm.
Can you hear me?
Yes, I can.
Okay, so as a student, in particular, I'm a student of geophysics engineer. So could you give us an advice based on your experience? What are some of the main troubles that you had being a student?
That's a hard question. Yeah, I mean, I think a lot of these questions sort of around career trajectory, what it is you want to be focusing on, what sort of skills you're really excited about. It's, you know, it's absolutely a personal journey. And I think I've been very fortunate to have mentors who really encourage me to, you know, follow the things that I'm interested in. Because it can be easy too to sort of really target a specific job. And I think a lot of that is kind of changing as, you know, oil and gas is not as prevalent as an option for geoscientists. There still obviously is a very important role for geoscientists to play. And even as, you know, the world starts to transition, having geoscientists involved and helping make responsible decisions about our subsurface resources, I think is critical. But yeah, I mean, I think it's figuring out what things you're really excited about, developing those skills, and then keeping in mind what are all of the different applications that you can you can be connected with. Is a lot of these skills, and one of the things I've really enjoyed being on the computational side of things is there's lots of overlaps with very different fields. So a lot of inversion theory, there's a lot of people who are geoscientists who work primarily in geophysics, but have actually done some work in medical imaging, for example, because you're looking at the same physical equations, but just a different scale and a different survey setup, rather than, you know, something flat on the earth that's around somebody's head or something like that. So there's obviously more detail, and you need to be working with like experienced medical professionals, but a lot of your skills are actually pretty transferable, which is kind of cool.
Thank you very much.
Does that answer your question? I don't know if that does.
Yeah, it totally answered it. Thank you very much.
You're welcome.
And don't worry, being a student is always hard.
Yeah.
Undergrad, master, PhD, all the time is a little bit hard.
Yeah.
Well, so I think there are no more questions. So Lindsey, thank you very much for being with us today. Thank you guys for participating, for asking so many interesting questions. Thank you, Kimi, for attending. I know you're not a geologist or a geoscientist, but we're gonna make a good geologist out of you, I promise. And guys, tomorrow we have more talks. Tomorrow we are gonna have Adriana Crisostomo Figueroa talking about, I will make a short name for the talk, that is turbidines. It's gonna be really interesting. And on Friday we're gonna have Jesper Drams talking about how he moved from geoscience to be a machine learning engineer. So I hope we can see you tomorrow and also Friday. Lindsey, well, if you want to join us tomorrow or Friday, you are welcome anytime. And Kimi, I don't know if you have any words.
Yes, thank you so much, Lindsey. I think something that I can take from today's conversation is the fact that you emphasize so much on networking. I mean, how this community is a result of the networking of different people with, let's say, one main interest, and all the things that can be created and has been created. And that's exactly, I think, something that matches with Chevening. Yes, not all of them are as Julio or as Tanya or as Memo, but they share one common objective, which is support Mexicans. So I think we can, the Chevening community, especially the Tabasco one, the one that come up with this idea of the Chevening Talks, can learn much about you, and I think we can emulate a little bit of what you have achieved so far. So thank you so much for sharing.
Well, thank you so much for having me, and please, anyone, feel free to reach out if you have further questions or thoughts or want to chat through things. I'm very happy to. And thanks for having me as a part of this. I'm very excited to have had the chance to share some of the work that's been championed by the SimPEG community. And yeah, feel free also to reach out to anyone in the community. And if you're excited about getting involved, we'd be very excited to have you.
Thank you.
Thank you, guys. And join us on Underground. I posted on chat the link to the Slack channel. Guys, that's great for networking. That got me to meet Lindsey a couple of, I think a month ago. I don't know, like 2 months ago.
Yeah.
And then we start like talking about what if we have a talk here for Mexican community, and here we are. So networking is important, guys. Geoscience, networking, and coding, go to Software Underground. I strongly recommend that. And thank you for being here. Thank you, Tanya. Thank you, Kimi. Thank you, Guillermo. And thank you, Lindsey. So I think I'll see you tomorrow. Tanya, Guillermo. you want to say?
Thank you,
Gracias,
guys.
chicos,
Thank
por
you to
unirse.
everybody.
Nos vemos mañana en otra plática
Bye.
de Chevening Talks.
Nos vemos.
Lindsey.
Nos
Bye,
vemos.
Lindsay, and thank you.
Thank you.
Thank you. Bye bye. See you guys. Hola, Jimmy. Adiós, Jimmy.
Se fue.
Nada, se fue. Ya se fue Memo. Bueno, yo creo que, bueno, ahí platicamos un ratito.
Sí.
¿Vale?
Sí.
Bueno, voy a comer algo mojado.
Sí,
Vale.
no te preocupes, ahí por el chat nos escribimos, lo que sea, y bueno, nos ponemos de acuerdo.
Sí, sí. iPhone de Daniela Ursul. Hola, Daniela.